Watchmakers Institute and fellow with the British Horological Institute. J.B. Ranch is located just north of Austin, Texas. Huckabee is retired, and the things that you will be seeing are related to some of the equipment, the clocks, and the repairs that Huckabee will demonstrate in this film. Look at the clock at hand. This clock is about almost 3 feet high. It was built by Birge and Mallory in the 1830s, the late 1830s, possibly 1840. As we look down this, we see a lowered door and a very crudely painted picture there. We come up to the central section. We see the home, possibly a lavish estate of a countryman in that period of time, and we look at the wooden dial. This clock was made by Birge and Mallory, and according to the paper that's in the rear of it, it was built in 1841. This was the era, the transition period between wood movements, wood clock movements, wood gears, wood plates, and the use of all brass movement. This particular clock is unusual in that it has what's called a strap movement. That is, rather than solid brass plates, it uses a series of straps that are riveted together. Further, the characteristic is that of the roller pinion. The roller pinion that was developed by Ives just a few years before. The profile of the wheel teeth is very unscientific, and to offset that, each one of the lantern pinions, that is the lantern wires, each of those trundles or rungs, as they may be called in some literature, is set on pivots so that they actually roll in the action of the gears. We will look into this particular clock. We'll remove the movement and go through it and see what was in operation in this 1841 era when brass was scarce and roller pinions was thought to be the greatest thing in the clock industry at that particular time. Looking at the rear of the clock, we find that the rear panel is 2 pieces of wood that are set together with tongue and groove. And if we look up toward the top, and I seriously doubt that this will be visible in the camera, but in the upper left region here, there is an inscription that says 1903, September the 29th, C. Armbuster, A-R-M-B-U-S-T-E-R, Sardinia, Ohio. I just looked up in the 1987 Rand McNally Road Atlas, and I find that Sardinia, Ohio has a listing of 870 people. It's about 50 miles east of Cincinnati, Ohio. Presumably, the name Armbuster, well, it says C. Armbuster, watchmaker, and presumably this was the marking that he placed on the repairs that he made that may be analogous to case marks that's used by AWI members at this period of time. Opening the doors, we see the pendulum swinging. The upper door is open. We can see possibly through the hole in the dial the upper limits of the pendulum. Down in the bottom, we see that this pendulum is a kind of a sunburst covering over a lead disc. This is about 2 1/4 or 2.5 inches in diameter, and there is a pair of 8.5 pound square prismed weights, cast iron weights, that's sitting in the bottom of the case. The swing of this pendulum here is not under power at the moment, as the weights are sitting on the bottom of the case. I'll pause here for a moment and we'll remove that dial and look inside and see this unusual movement. Into the movement, we see that the framework is skeleton in nature, and that each of the wheels have kind of unusual windows cut into them. And what makes this look unusual, the spokes of these wheels appear to be as a Gothic architectural column. And then stamped into the periphery of those wheels is a stiffening ring out near the teeth. The tooth profile is radial on the tip. It is a radius slightly off of center of the axis of rotation for one side of the tooth, and it's a radius a little more off center, off the center of rotation for the other side of the tooth. The outrigger that goes to the extreme left in the central section supports the arbors for some of the striker control components. A pair of wood screws in the very back, and may not be visible in this particular photograph. Those screws hold a block that secures the upper portion of the movement into the case. The seat board, which we see in the lower area of the photograph, that seat board is keyed into some structural members of the case. By removing those screws, it's up in the top, right in the very top of the photograph at this point. By removing those, the movement will slide forward, that is, toward the viewer, and can be slipped out of the case. Of course, we have to take the ball from the pendulum and best let the pendulum rod be completely detached from the movement. And we have two weight cords. One is going almost straight up to the rightward edge of the movement. The one on the left side goes out almost horizontal, then up and over pulleys in the top of the case. Now let's take a look in the Birge Mallory movement. We have it out on the bench. We tip up so that we can look a little closer into the face, and we see the escapement mechanism here, the escape wheel right in the top of your picture, the anchor. And we'll begin by removing some of these pieces. We slip aside a little hold-down wire and lift out the escapement anchor. And underneath that escapement anchor is a small screw and a bridge which adjusts the depth in there. Let's look at the hand situation, and we'll remove the hands. We just very carefully draw out a pin here that appears to be a portion of a small nail, and the hands should lift off. Lift the hand off and the cupped washer, and we will wring off the hour hand. Now, looking a little further, we cannot stand this movement on its base here. This is the seat board, because this wire coming out the bottom terminates down here in the striker gong. That presents a problem in standing this on its feet. So to correct that situation, we just reach over here and we form that striker hammer, the hammer wire here. We form that up so that it's no longer in our immediate path, and that will solve that situation. I notice in the movement right here at the top, right in the top, that there is no taper pin in that pillar. These are cross drilled for taper pins. This one has a cut brass pin in that pillar. Down here appears to have a little nail that's had the end turned over on it. It doesn't fit very well. There, we've slipped that out. And let's see what we can do about slipping out this one down here. I believe that one's going to come out readily, and we can slip the one out right over here in the striker mechanism area. We don't have to be concerned about disassembling the movement under power here, because when we remove it from the case and the weight cords are unhooked from the weights, there is no power in the movement. I notice the weight cords here appear to be very strong twisted nylon lines. These are probably in the order of 75 to 100 pound test lines, about 80 thousandths of an inch in diameter, I suppose. And that's the type of line that you normally would not put on a weight-driven clock. The reason being, if you place the weight on this line, the weight will begin to spin, and it will spin until the line is completely unwound, and that weakens everything, and you'll ultimately drop the weights. In this particular clock, that's not a problem, because the weights are square in section. That is, if you look into the top end of them, and they follow a fairly close-fitting weight chute in the case, so the weights cannot spin. Actually, what this does is keeps the weight just barely touching the woodwork of the case, so that there can never be any sympathetic vibration of the weight that's set off by the escapement. Now, let's identify some of the mechanisms here in general terms before we begin a disassembly. Over in this region, this is the time side. This is the great wheel for the time side. This wheel carries the ratchet, the winding ratchet, the click, which is out of view, back in behind here, the click spring, and the weight hoist drum that the cord is wound on. This hoist drum is about, well, let's see what the diameter looks like on it. That hoist drum is 920 thousandths of an inch in diameter. That's just a little bit over 7/8 of an inch in diameter. Presumably the one on the other side is the same. We drive from this great wheel into a pinion here that would take us into the second wheel. This is not seconds, it's the number 2 wheel. All right, the second wheel, the number 2 wheel, its teeth drive into the pinion, which is in behind here, which is in the third wheel, and the escape wheel is the 4th wheel. Let's see if we can get the movement where we can see the escape wheel. The escape wheel is the 4th wheel. This is the 4th wheel, the 3rd wheel, the 2nd wheel, and the great wheel are the first one. Like many American-made striking clocks, this has an indirectly driven center shaft. The center shaft has a wheel behind, and then behind the movement we can see that situation. Get about here. This gear right here, possibly you can't see the teeth around the periphery of that. This gear ring, it's a hollow, empty in the middle. This gear ring right here is attached to the second wheel and meshes into a gear. This one right here, maybe we can see it a little better right there. Meshes into that gear, which is fit to the center shaft. This is called indirectly driven center shaft. What you see somewhat bright right in this area in the photograph, that is a plate, and I'm not sure I can identify it at the moment. It appears to be a tin-plated piece of steel, possibly is zinc. Sheet zinc was very frequently used in clocks in this period of time, but that is the friction washer that permits the hands up on front to be turned to set the time. When I turn the hand, then the train spins simply because I have already began to disassemble the escapement. But that is, it's a square that's inserted into the heavier, thicker gear here that permits us setting the hands. Now that pretty well identifies the timekeeping train. The one remaining factor is that we have not identified what drives the hour hands. Hour hand. Up on this center shaft, down in the central region here, is a pinion about a ½ inch in diameter that drives a gear that's deep in between the plates. That's this one that the pencil point is on, right here. And then it carries a pinion that meshes into this wheel here. This wheel is fitted to the pipe that the hour hand's on. So this is the 3-to-1 center shaft, center pinion here, down to this. There's a 3-to-1, and then from the pinion underneath here up to this is 4-to-1, making the 12-to-1 reduction for our center shaft. And that's the entirety of what we find in the time train. The pinions here are, many of them are of low count. For instance, the escape wheel up inside, the escape wheel, this is the escape wheel arbor's pivot right here. The pinion on the escape wheel arbor has 6 teeth, and one of the most unusual things that I have encountered in clocks is the pinion over here that's on the fly. Let's look at into the striker area here. We're looking at the striker fly here. The pinion that is at this point. That pinion only has a count of 5. A count of 5. That's an inordinately low number, and had this not have used roller pinions, it's entirely possible that the gearing would have not been functional using a pinion count of that low. Let's slip some of this apart, see what we find inside. You recall in the little time-only movement that we started by carefully lifting one of the plates from the pillars, and we'll do this, and I can't lift that. And the reason that it will not lift is because right here in the central region there is yet one paper pin, one more pillar right in here that we have to get out of place. Now let's see if we can begin to lift this plate. Okay, we lift up, and we lift up. This is such an unusual movement. I obtained this around, I think about 25 years ago when I lived in Lexington, Kentucky. This come from an estate sale that was held somewhere around the Lexington area, and the elderly gentleman that was the auctioneer, when this clock went on the block, so the story goes, they had no bidders. No one wanted it. It somehow was just out of vogue among the representative group that was there. So he placed an opening bid himself for the clock, and there was no bidders, so he carried it home with him. And a few weeks later he sold it to me for a price that today would seem totally, utterly, completely unbelievable. It was so low. Let's look at this plate. I don't know if you call this a plate. I am really at a loss to know what to call this. It has the analogy of the clock plate. It also has the analogy of a bridge, that is a type of bridge movement, but this assembly is riveted. There's 4 rivets right here, 4 over here, 4 in each one of these crossovers. So being this is not disassemblable, I suppose it's not technically not a bridge movement, and it's really anything but a full plate movement. But that's how the plate is made. This is rather heavy. This is a rather heavy piece. If we look at it, I dropped a rule on this a few minutes ago, not literally a rule. I laid a piece of writing paper on it. This piece of writing paper was 8.5 by 11 inches, and this dimension right here, no, that's not exactly right. This dimension right here, the length of this base right here is equal to the breadth of a piece of writing paper, which is 8.5 inches. This is probably in the order of about 6 inches. Let's look at the dimensions on it, just as a matter of academic interest. That brass right there is about 90 thousandths of an inch thick. Looks like it's about the same as I measure it in other places, about 90 thousandths of an inch thick. And let's look at the width of it. And the width of it, well, the width of it is about 570 thousandths wide. It's a nice fat ½ inch, 500 thousandths being a ½ inch. There's an unusual situation. This is made in the transition period between brass clocks and wood clocks. And we noticed that the plate was pinned in place around the pillars. Each one of these pillars has a pin. And I think I am correct. We'll look at this as we go further along. This screw that holds this little bridge right here is the only screw in the clock. That's the only screw in the clock. If we turn up and look from underneath, right under here, we find that there's a J-bolt. This is a J-bolt here, and a nut, a J-bolt and a nut. And those J-bolts tie these lower pillars down to the seat board. Now, as we look at that, and I believe I'm correct here, that is the only nuts, 2 nuts, that's in the movement. It has the J-bolt, which appears to be just a piece of heavy wire threaded on the end. And those nuts are undoubtedly handmade because they're approximately square and they are not of the same size. For all practical purposes, you would have to turn those with a plier to get them out. This piece dropped out of the striker mechanism over here. But for the time being, let's look at the gear train. Here is the escape wheel. Let's see if we can move something out of the picture here. We look at the escape wheel. This wheel is rather heavy for a movement of this type. It has a recoil escapement. The teeth show us this is a recoil type escapement that we're using. And the pinions are roller pinions. These pins are rungs or trundles. They're called a variety of things. But as I touch these with the tip of this pencil, each one of them is loose and it has end shake in it, just as you would expect to have in one of the movement arbors. Let's try to get an idea on this thing. These are, let me measure that again. What's catching my eye is the diameter on it. I measured one of these that was 61 thousandths of an inch in diameter. Most of them are about 65 thousandths of an inch in diameter. You recognize that 62 or 63 thousandths is the round number for 1/16 of an inch. And so those things are approximately 1/16 of an inch in diameter. These discs that are drilled on the end have this trapped, have these are called lantern pinions. We might envision this as being the jailhouse bars or the grid wires or whatnot in a lantern cage. And the discs that are on the end, these are called shrouds in most antique clock literature. Kind of nicely made, ornate, nicely made hub right here on the gear, but the staking job of fitting the wheel to the hub appears pretty crude. But I think that is, I believe that is original in that wheel. Let's move down to the third wheel. Look at the third wheel. Let me see if I can get an image of one of these spokes in here. If we look at this right here, this section of this spoke, and then we notice that the spoke is neck down, smaller here, gets larger as we go to the bottom. That has the image of a capital, or the cap over some type of large column in a piece of architecture. That must have been the person that designed the tools that cut these windows out of here must have had a great appreciation of architecture that had large columns with some type of grotesque capitals at the tops. Again, we have the lantern wires. These are roller wires. As I do this, I could roll. Each one of these will roll in its position. When I think about this movement, I think of the quantity of pieces that is required to build up a movement like this. This has 6 of these individual wires. It has the shroud is 7, the arbor is 8, the hub is 9, and the wheel proper is 10. So we have 10 pieces. It requires 10 individual pieces to be assembled to bring this wheel here together. This one right here has the same number of pieces. Now, let's think about the teeth, the profile of the teeth in this wheel. Let me obtain a stick rule that we can use as a pointer here, and we'll look further. Using a little stick rule, I'm going to set that rule approximately in line with the face of this tooth, and let's see what it looks like. Right here, I have the rule, this edge of the rule, right against the face of that tooth. And if I project that rule, that edge of that rule, right down, I would pass through the axis of rotation here. The perspective on the camera may not be too good here, but this line on the face of that tooth would pass right through the center of the axis of rotation. Now let me do the same thing on the other side of the tooth. All right, we have the rule now lined up with the back side of the tooth. So this edge would pass approximately here, somewhere out in the order of about 2/10 of an inch away from the axis of rotation. So you see, the forward face of this tooth is radial to the axis of rotation, and the rear side is a back slant. Now, let's see if we can look at some of the measurements. I'll see if I can measure the breadth of that tooth right out by the tip. Breadth of that tooth is just in round numbers 140 or 145 thousandths of an inch. That's the breadth right out at the tip. The tip of the tooth is radial, is a radius right off of the axis. Down at the root, I think I can get into the root a little easier here. At the root, it's about 157 or 158 thousandths, and the space, see if I can get into the space between it down there. The space is about 174. So the space between the teeth is wider than the tooth itself. And that rolls in mesh. That rolls in mesh with this lantern pinion, and it runs remarkably free, just remarkably free. Take up the next wheel. The next wheel is a repetition of the same situation, only it's a bit larger. And as we look at that wheel, tooth count is greater, it's larger. The pinion has an 8 count. This has an 8 count. Let's see how these roll. This is pretty gummed up. Yes, they all roll. I noticed, well, I've had this clock about 18 or 20 years, and I did a little bit of work on it when I got it, put it into running order, and I know that the lubricant that's on this is that age, because I've never run the clock, but just a short period of time after that it was obtained. It has a pinion count of 8. On the back side here is the ring gear, this being a ring. That's the ring gear that will drive into the center shaft. Let's look at the center shaft, the ring gear, and the center shaft as a combination here. This is the combination that we have getting into the center wheel. This white looking, that looks like that it's tinned, tin lead solder tinned onto a spring steel piece there for friction purposes. This wheel here drives into this arrangement. See if we can get these together like that. That goes into that type of arrangement. This is center shaft, drive 3 revolutions here to 1 of this, and then 4 revolutions here to 1 of this. Gives us a 12 to 1, and we exit on the hour wheel pipe. That sits into the central section. I have to get in a little closer to see this. That sits into the central section of the movement. We're taking this apart without regard to where things go. When we go back together, we'll do something like we did on some previous work, how to find the way. The great wheel. Ratchet, click spring, hoist drum, and the great wheel has the cord attached. That wheel is hollow up inside. I don't know if I can reach this up here or not. Let's see if we can pull that cord out. Well, I can't pull it out very readily there, but the object is this cord is pushed back into the drum, caught up with a spring hook or some type of little hook, and pulled out, and into the hand has a knot tied in it that secures it in place. To disassemble this, here's a friction spring, cross pin, that would be pressed down, pin taken out, great wheel could be removed, and etc. We'll lay this aside. Wind some of this cord up. Lay that aside. Looking around here a little further. Here is a spring. We're attempting to identify what some of these pieces by function. Here is a spring that kind of a grasshopper spring. Comes over here, makes a turn, latch down to the movement, passes through a hole here, and that imparts the motion to the striker hammer. On this, if we look at this assembly, of course the arbor, the wire that goes down to the gong, and the hammer at the end of it, and this hook right here is just pure and simple a stop. It stops off on some of the mechanism here to when you drop the hammer, that limits the distance it can travel. Then the stored energy flexes the rod a bit, and the overtravel goes into the gong. This end right here is where the hammer lift pins pass this end of the hammer to lift it and then drop it, much in this manner. Look at the fly. Some interesting situations on a fly. There are probably more striker problems that's traceable to this simple little mechanism than almost anything that goes on in a clock. It's called a fly, I suppose because it buzzes, and what this does is governs the speed at which we strike. It just paddles the air and gives some resistance to keep the striker mechanism from racing. This has, as we noted, the unusual pinion count of only 5. This arbor is pushed into the fly like this and latches in place. When the arbor was made, there's a little groove turned right around here, a crossbar that's just mild steel. It's flipped over on the back side here to keep this in place, and a V-notch. And the way you get this in, you just cup the fly a little bit, go in here and latch it, and it's like this. Now, there's 2 things you must have. The criteria that we must meet for this to work, and there can be no exception if it works good. Number 1, no matter how fast that you start this off, the friction here has to be great enough that the arbor does not slip. If the arbor slips, your striker races, your count mechanism, your stop mechanism, you will overrun its ability to control, and your striker will get out of step. It may strike most any time or whatnot. On the other hand, when you stop the striker mechanism over in the movement, when the striker mechanism is stopped, this is turning at a rapid speed, turning at a very rapid speed, and the stored energy is such that you must have relief or it will tear up something in the mechanism. Almost without exception, if you find a fly that is too tight in the pivots here of this general type of clock, I don't specifically mean a Birge Mallory with this type of gearing, but the general American made 8-day so-called antique striker clock, you will find that wheel will eat these pinion rungs up rapid. It will tear that pinion up. What happens, you go into a stop. The striker mechanism is stopped. This is so tight that you dissipate your energy. You dissipate that impact right in your pinion wires, and it tears the pinion up. So it must be able to slip, it must be able to pull, and it has to function in both of those modes.
little further, take out some of this control mechanism, and we'll look at this. This is a part of your control mechanism. This pin here is the stop word. When we reach the end of the period of strike, that pin is where that we will stop the motion of the train, and we stop it abruptly. And when we stop it abruptly, we have the shock on the fly. Okay. This cam right here. This cam, the purpose here is to test our count wheel. And the object is, do we lock up? Do we lock up after this strike, or do we go another one? Do we lock up, or do we go again? This makes a revolution each time that we strike. So we have a feeler that rides in the cam. And let's see if we can get that cam in a little better view here. Possibly right there, that we can see through the corner of this cutout. We have to satisfy two conditions in order to stop the striker. One is that our feeler here is in the stop position. The second is that our feeler in the count wheel is in the stop position. We'll discuss those in more detail when we go to reassemble the mechanism. Let's look at the back side of this. This is our hammer lift pins. Hammer lift pins. And this hammer lift pin, the hammer, find the hammer here, this hammer tail that we have here rides one of these pins. And we lift and we fall. And we lift and we fall. And going past these pins is where we get the hammer stroke. We said that we test for the stop here. So that says that if we test here each hammer stroke, and this is where the hammer strokes originate, it says that this wheel must turn one revolution in the period of time that we pass between two of these pins. Let's take a look at this situation and see if that looks right from a logical standpoint. We have 2, 4, 6 count pinion. We start here 1, 2, 3, 4, 5, 6. So you see we pass 6 teeth in this wheel, we pass 6 in the pinion. This makes one revolution. Count again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's the origin of the ratio, and the ratio that these must run together. When we go to assemble this, there's an order that we have to have those in. Look a little further. This is probably the most complex piece that is in the entire clock. If we look against this, look about the same. Look just about the same. Matter of fact, if we were looking at these without very careful examination, we would say that these two wheels are the same. And I don't think there's any doubt about it that when they cut these wheels out, the tools that they cut these two wheels out, at one point when they were initially cut from the sheet brass, these two wheels were identical. But let's say that the second operation, of this might have been to cut the teeth. I would think that would be the logical way that this would be done. Let's see if they remain the same. Here's a stiffening rib that's stamped in the wheel, stiffening rib in the wheel, same diameter. Let's look at the teeth here. These teeth point leftward. As I look at that, these teeth point leftward. These teeth over here point rightward. It says that if this wheel went in the wheel cutting engine like this, see with the groove, stiffening groove here, you got the teeth cut, this one had to go in the wheel cutting engine in the opposite direction in order to cut them in the opposite, to lean the opposite way. So there's a subtle difference between the two. Look a little further. Note that this is a ring here. That ring is called a count wheel. Well, looking through some of the old literature, you may find that even that is a misnomer. This is one of the reasons that I kind of steer clear of specific calling names on these things. A count wheel, I suppose, was a wheel that counted the striking. A locking plate, what is called a locking plate, is a plate or a disc that counted the striking. It gave the strike count. A count wheel and a locking plate have the same function in a clock. We call this the great wheel back here. This must be a locking plate because there is no teeth. There are no teeth on this particular ring here. Notice that there are notches in it, but these are not. This is not gearing. That's not gearing at all. So this appears to be, the proper name would appear to be a locking plate in this particular clock, though it might be called the count wheel assembly. It might be called the great wheel assembly. Those types of things. Now let's see what these notches mean. Notice here's a wide one. Right there's a wide one. And then here's a little narrow projection and a space, and a little wider one, and a space, and it gets wider and a space, wider and a space, and so on. To identify these, this is a place, we have a feeler that goes in here that stops the striker. If that feeler lands on the periphery, we go for another strike and retest, another strike and retest, another strike and retest. At this point, going back this way, this is the sector that counts the 12 strike. This next sector counts the 11 strike, and the 10, the 9, the 8, the 7, the 6, the 5, the 4, the 3, the 2. What counts the 1 strike? So we come down to counting 2. What counts the 1? Well, when the 1 strike starts, it cuts off immediately. So we have empty space is what this amounts to. In reality, this will be a space and the counts, a space and the count. Looking at this, this represents 12 hours right here. Continuing around, we repeat the same situation in this locking plate. Now what do we conclude? What do we conclude from that wheel? Well, we can draw some absolute conclusions on this. One of these absolute conclusions is that we have 2 sets of 12 strikes in 1 revolution of the wheel. We have 2 12s, 2 11s, 2 10s, 2 9s, 2 8s, and so on. So we conclude that this wheel, that this assembly, turns 1 revolution per day. No more, no less. If it turns more or less, the striking will be an error. So we can say in very specific terms that this wheel turns 1 revolution per day. Let's look at another conclusion we can draw. We pull this cord around here to exactly 1 turn. I pull this around to 1 turn. We pull it out here. This is how much weight fall that we will have in a day. Distance that I'm holding in between the tip of my finger and up here. Let's see if we can measure this on a stick rule. It's 3 inches. Maybe a little more, a little less in round numbers. It's 3 inches. That says that the weight fall on this drive mechanism is 3 inches per day. It says that in 8 days the weights will fall 24 inches, and that says we have to have a tall case to handle a heavy weight. And we look at the cordage that we have here, and we can see that that's the situation. Those are some conclusions that we can draw just right out on the surface of situations. Now let's consider reassembling some of this, just in a piecemeal thing. We've laid these wheels out without regard to where we got them or anything about it. Let's find our way back by just intuitive logic, as we did in the movement in some of the earlier tapes. This wheel is not a time wheel because it has a locking plate to control the striker. We can set that aside. We're going to work on the time side now. We'll work on the time side. So that one's not in our business. This one has the hammer lift pins. That says that's striker. We can lay that aside. This has the pins for the cam for some of the striker control mechanism. That's the wrong wheel. We look at the fly. We don't have a fly in the escape mechanism, so we set that aside. Now let's continue down and see what we have. We've got another great wheel here. We only have two. That's the time wheel. Clear and simple. We look at this, and from the identity of the square and the hour hand pipe, that's the center shaft of the movement. That goes right in the center hole. No questions asked. That's bedrock. Let's look at this wheel. It has no striker identification, so it must be somewhere up in the time train. We put it over with the time train. This one has gear on the back, and we have to get from the time train into the minute hand, hour hand shaft, so these have to be associated in the time side. We only have one left, and that is down in the midst of the movement. That's the one that is in the hour hand reduction train, and we would identify the escape wheel very readily by its pointed teeth. So we have in this group over here the wheels we would have. Let's discuss another interesting situation here. Over here in the striker, we find this locking plate. Let's look at the diameter of that hole. The diameter of that hole is about 3.1 inch. Let's look over here at this. See that? Undoubtedly, when this movement was manufactured, that wheel was removed from that locking plate. That wheel was removed from that locking plate. That's just a pure and simple good decision in manufacturing and the conservation of raw materials. Let me cut the camera here a moment, and I want to see if I can locate something else along this subject matter. Here's a winding key, and this winding key says right up here on the face of it, it says E. Ingram and Company, Bristol, Connecticut. Now, I don't know the age of that key, but that must be an old one from the looks of it. But over the years, the study of a winding key has been a very interesting thing to me. There are all types of ornate shapes that go around winding keys, and a diversity of shapes of holes that are in the center of that key. What do you think that hole is? You think that hole is there just to make it feel better for your fingers? I don't think so. The movement that come from probably had a pair of pinion shrouds that come out of that key. I've seen a number of keys that have the image of a click pawl in each side of the key. You need one key for the clock, you need two click pawls. You can get them right out of the key. It's entirely possible that right off of this back curve right here. See, if you would extend this back curve in your mind up here a little bit, you get a click pawl right out of the neck of that key. That's an interesting thing that I thought I would comment on as we pass by. Let's get back to the time train. How does this go together? Well, what did we say on the little movement here some time ago? First wheel goes first because it's the biggest one, second wheel goes second because it's the next biggest one, and the third wheel because it's the next one, and the escape wheel. We line them up here. Let's see if we can get them where we can see. The big one, the next biggest one, the next biggest one, and the next biggest one. Over here we got center wheel. We'll deal with it a little different. That is reduction train. Okay, that's how we identify them. I don't propose that we set these in the train in that order, but that's how we know what they are. Great wheel, thought process, great wheel. How does it go in? Winding key has to go up. Winding key faces us. This is top side being the side of the clock that you wind the key from. Second one size, drops right in the hole, has to mesh with the pinion. Cannot go this way, cannot go that way, because the pinion would not line up. Next one, same situation. Find the way, right there. Next one, find the way, right there. Bigger, smaller, smaller, and the smallest. Go over here and look at this. What do we have? We say this one has to go right in the center. In order to get in there, it has to go underneath this one. There we are. And this pinion has to mesh with this little wheel that's right under there. So it has to go little pinion up. Okay. If you're a beginner in this situation, you'd like to practice a little bit, let's just cut off here and practice a little bit. You don't have to have everything in the movement to see some of the features of it. Let's let this down. And as we discussed in the little trapeze movement, how do we get all these lined up at one time? Well, this one's really pretty easy because see, we got a couple of tall ones that we can line up, and we'll go right in here. And no, that one's not next. We're looking for the next one. The next one. There we go. That's the next one. Slip this one in. Slip this one in. Slip that one in. What's holding us up now? We've got some kind of problem here that we're not going down. It's not that. Not that. Not that. Doesn't seem to be this. That's down. This is not quite down. Right here we're not down. Right here we're not down. Here we're not. Don't know whether we've got a problem on the pillow. Yes, I believe that's what it is from the looks of it. There we go. What do we have here? Look at this. See how that operates? That's how easy it is to drop one of these things together. Simple, simple. I would counsel you, if you're a young clock repairman, young meaning somewhat a beginner, that as you assemble these things, don't try, if you have some identity problems, don't try to go the whole hog, a piece of it. Look at this. Look how free this train spins. It's remarkable, remarkable how this spins. I'll pull this cord right down here just a little bit and look at this. This movement was built in 1841 according to the paper in the rear of the case, Birge Mallory Company was only in business, I believe it was from about 1839 to about 1842, according to some of the historians. But here it is, 140 or 150 years later, almost 150 years later, and this movement still works very, very nicely. Let's slip this off. Try a little activity over on the other side, just to keep these train sections separated. Let's go over here. Let's inspect this piece. Out here in the light somewhere, and pick up an item. See this L-shaped pin here? Don't know if we can get that better or not. Possibly right there. This L-shaped pin right there. This is the center shaft. Turns 1 revolution per hour. 1 revolution per hour. We've removed the hour hand pipe from it. This is the hour hand pipe. We have a feeler out of the striker mechanism that comes over and rides this piece here. Normally rest about here. Come around, you lift it, and at some point while you're making this lift, we ready the striker to sound the next hour. When we drop off of this L-shaped piece, when we drop, then we strike the next hour. This is the device that carries the intelligence of when to strike from the time side to the striker side. Let's try this assembly situation like this. Put the big one in first, next biggest one second, next one third. That one goes underneath. We have to do a little pickup here. No, that's something wrong here. Goes above. I was mistaken there. And the fly. And the fly. Let's try the same situation assembling this. We have lesser number of pieces in the strike side. We start down on this. We get the first pivot very easy. It's a tall one. What's the next one? Number 2 wheel. Next one. Number 3 wheel. And it looks like the fly is holding us up a little bit there. Number 3 wheel. Number 4 wheel. Looks like we're not down there. We're not down here. There we go. And are we here and here? There it is. Let's see what we get. Pull the cord a little. Look at this. See how nice and free that runs. Just fine. Just great. Okay. Now we know how to do everything. Getting the time side together, the strike side together. We do this all at once. But we do not have the controls that controls the striking mechanism. And that is probably the more difficult assembly. And there is a pair of these right over here. This is the striker control mechanism. This is the hammer. And we will have to learn to do these things simultaneously. The controls, the striker train, and the time train. Let's cut the camera off here a little bit and let me rearrange some of these things so that possibly we can see them better, and we'll go into this a little more. Well, let me talk just a little further here first. How do we identify some of these. How do we identify where this goes against where this goes against where this goes? This one, against this one, against this one. How do we get that? Let's look for some identifying features. Does this go here, like that, or like that? Or does it go here, like this, or does it go here, like this, or does it go here, like that, or here, like that? We have 6 possible places, 6 pivots, 6 possible places that these pivots will fit, and it only goes in one of them. How about this one? There, there, here, 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 or here. Try this one. That, this, this, or this. What's the possible combinations? We've got 6 times 6 times 6. I don't have the calculator here, but 6 times 6 is 36 times 6 more, 360 or whatever it is, a number of possibilities that we can put those in. Now, we're just not going to try out all of those combinations. So let's pick up the key identifying features. Some identifying feature that will show us where they go. The reason I'm belaboring this situation is to develop a thought process. And if you use this thought process all the days of your life, it'll always carry you straight. Number 1, it's highly improbable that you would take the striker gong out of the side of the movement. A few clocks do, but it's highly improbable that it would happen. Recall in this one, we said that we will bend the striker gong, not striker gong, the striker hammer, that we would bend the striker hammer up away from the seat board so that we could stand this thing on its feet, like this. That says that this could only go one place. It could not go that place because we can't get it back in there. It must go this way, right here. We also said that there's a spring here that this operated with. So this one goes in this position. We'll remember that. We got that one straight. The thing that I did not show you when we pull the movement out of the case, as a matter of fact, I removed the movement from the case with the camera off. But there's a little push-pull rod hooks into this eye that hangs all the way down into the bottom of the case, into the pendulum area. And by giving that rod just a little jiggle, you can advance the striker one position, 1 hour position. That push-pull rod hooks in this eye, right here. This little eye, right there. And that hangs out of the left side of the movement. Now that would pretty well tell us that it has to go this way, this way, this way, or this way. That narrows that situation down. Let's look for another identifying feature. Let's look for another identifying feature. Let's look for this little, let's see if we can get that in the camera here somewhere. Right here. This little spade-like tip. That little spade-like tip right there. This wire comes out here. It's flattened to a very thin wire, turned over at an angle of about, the internal angle here is about, probably about 80 degrees. And this is about 3/16 of an inch wide right there. What is the function of that tip? If we can identify any one of these three tips, we can identify where it goes. This is your count wheel feeler right here. Get back in the picture. This is the feeler that is feeling for the notches in the count wheel. See, as the count wheel turns, locking plate, we called it locking plate up earlier. We decided we'd call it locking plate. That's the feeler that feels for that wheel. Okay? You already know where the great wheel goes. Let's try this. Does it go that way? Or does it go that way? We bring this tip to the periphery of the wheel. It would have to go there or here. Now, being that this is attached almost exactly in the center of the arbor, you might say, well, it would approximately reach the locking plate either way. But recall, if we have these two projections here, pointing out to the left of the movement, they could have no function in the movement. They have to be inward, like that. So we have a positive identification. Looking at a little logic, we have a positive identification as to where this would go. How did we know that it does not go up there? Won't reach the locking plate. This won't reach the locking plate. It must go here. Simple as that. Okay. Our remaining one, is it there or is it there? We find that both of these are essentially straight. We find that this is an open movement, so let's just don't worry about it. We'll put it in later. See, many of these things say, don't worry, we'll put them in later. Let's start together with the movement. Put the hammer in place, right here. We saw we unhooked the hammer spring later, so let's not hook up the hammer spring right up front. Another great wheel. We go on the assumption that we can get the weight cords fished out one way or the other, even if they fall in the wrong place. Locking plate, strike side. No locking plate, time side. No hammer lift pins, time side. No distinctive striker mechanism, time side. Striker mechanism here, that side. Why did I move up two? I have one wheel that's larger than that is, down here. Move up another, move up the fly. That fly is a little tricky here, so let's just don't put the fly in, for the time being, that is. Center wheel, our pipe, down under. That one should have gone in first. Down there. This one should have gone above it. Learning a lesson here. Get out, get in. Get in, and another. Come back with this one. Okay. This one goes here. This one goes in the escapement position. All right. We want this one to go in place. That one would be difficult to put in later. So we drop that in right now. Got some problem with this. It's way out of range of being able to do any good, looks like. Let's see if we can get this down to about where we bent the arm up. About where we bent the arm originally. this tail right here must go under this plate, because that's where the lift pins are. So we'll kind of scoot down under here, go in the hole right there. Let's see how we're doing. 2 pieces short. Let's see if we can stuff those in later. 3rd piece short, we'll put those in later. Let's try this. Go over the longest shaft first, next longest shaft, next longest shaft, let down. And we begin to work our way down on this. We're beginning to line up on some of the pivots. Now, the trick is to find who is next. Who is next? I'm kind of favoring this time side here, holding down on it a little, looking for who is next. And I don't really know where it is. Right here. Next. Is it here? Is it? No. I've got something that's holding me up and appears in this general area. And can't see where it is. I believe it's this little one. Nope. There we go. It was that one. And let's try the hammer. Hammer is approximately next. I don't believe it is. I think we've got all these in. How about this one? That's next. And how about that one? Get on a pillar. Pillar. Now let go here. We will probably spring up and get something out of place. Feel like I'm heavy right in this area here. Now let's down more, I think. We're approximately down there. Now, there we go. We're getting mighty, mighty close. Notice we can run the time train and run the strike train. I'm going to turn off here for a few moments. The thing that I need, my taper pins, I only have really just one good pin to go back into this movement. I'm going to see if I can locate some pins to go in these pillars, and as soon as I can locate some suitable replacement pins, we'll come back and we'll finish assembling this. Remember, we've got to cope with this, the escapement, and I don't know whether we saw these things. This is one that we have to cope with. This is one. This is one. And the escapement anchor. Also, we have to have the proper timing relationship between all of these control devices over here in the striker. And working that out is another problem. So let's locate the pins and we'll continue a little later. Turning back on the camera, I've been away some 15 or 30 minutes. I stepped out to get some taper pins. This is brass taper pin that we have here. Let's see if we can find a place that we can look at this. They're made out of brass. They're about 7/8 of an inch long. These are pins that we'll use to slip in these pillars to hold the movement together. We'll slip one there for the time being. Slip one down in this corner in this pillar. and that pillar's not quite down, so we can't place one there. Let's begin to latch this movement up together, see if we can get things in time and working. Now notice right here, got a problem with the hammer. Let's slip that in there. Here we are. I believe that's the position that the striker hammer goes. We recall that by we formed this wire up in this position when we had that open. Now let's look into some more of this and see what we've got to do to logically get this in order. Do we place this one in first, this one in first, or the fly? Back in the camera here. Which one of these are we going after first? Well, I suppose the one that with the kind of the general rule is do the tough ones first. Let's try this. Let's try to imagine where it goes. The point I'm attempting to teach here is not the look at this and say it remembers it goes in such and such a hole. We want to remember that it goes somewhere for a reason. For a reason. We said that this piece, this projection right here, meshes with the count wheel. Let's drop this onto that pivot position and look around here and see if we can hypothesize where it goes. If it goes on the count wheel, would it be about like that? Or on up like this? Down in this region? Where is it? Well, we know certainly that that goes on the count wheel. We know certainly it can't go against the count wheel out there or out here because it's some of its features would hang outside of the movement. So it must go in here like that, at that angle. So it's in there at that angle about here. We've got a problem in doing that. I can't stick this up through this hole. Maybe we can put it back through this way. I don't know. Can't get it in there that way. I can't get it in here this way. We've got this out in our hand. Now the question is, do we tear the movement down and go back to do that? And the answer is no. We just reach over here. This movement frame is pretty flexible. Reach over here, we lift up on the frame a little bit, slip that under there, right back in here. Got to do it some more, like that, and let's see how that we look here. And I think what we're finding is that's going to do us okay, right there. Now, how do I know this is okay? Let's look right here. This projection is riding this striker control cam. This projection right here, riding the locking plate. The other projection standing out in the middle of the air up inside. Now let's try this one. Does it go here? Or does it go here? All right, let's look at the projections and see the functions of them. What does this long one do? So far we have made no communications with the time side of the movement. This one is long enough to reach into the center wheel of the movement, down in here, to the L-shaped projection on the shaft for the striker control. When this turned up here, can reach the projection, the stop projection on that wheel. So it must go that way, not this way. this way. We just drop right down through this and see what we have. Looks like that's pretty good place, but not quite. I pull out and do it again because I had a little conflict, and I've got a conflict again. There we go. Find the passageway into the center wheel. Now let's see if we can get some of this back together. Let's drop the fly in right now. Looks like that's a good time to do that. There we go. How about this one? That's not the hold up. How about this one? Is that the hold up? I believe it is. Where do we go now? Where do we go now? Not that one. Maybe that one. I believe it's this. That's over in the time train. Don't really see where the holdup is. Here. Part of it. Here. Part of it. Getting closer. Here. Getting closer. How about down this way? This is getting closer. Closer. Try that. Try that. We go together. Here we are. Now, what's the problem? What's the problem? The problem is we're assembled without regard to any timing relationship through that striking mechanism. That's the problem. The striker won't work. Let's pin up the some of these things. We'll slip a taper pin in there. Snug that down. Snug this one down a little. Slip one in here for the time being. Now let's concentrate on this striker mechanism. Let's see what we can do to work out the problems in the striker mechanism. Yes, the train turns. That's okay. We pull this, we can roll the train. But let's begin. Let's begin by moving the camera. And let's get a look, review possibly a little better so we can look at this when it's standing up. Maybe that'll help us some. Let's begin by rolling this train and bring the situation to the end of a strike. I can't even roll the train right there. Let's see what we have here. Here we go. Now watch the striker hammer. Need to move the camera a little more. Right here. Watch the striker hammer. Let's turn the train and we strike. We want to stop immediately after the end of the strike. That's important in the system. We want to stop immediately after the end of the strike. The purpose of that is to provide what's called a run at the strike. We don't want this hammer to be partially lifted or in the process of being lifted while the striker is starting, because as the oil gets a little tired, it'll be sure to fail to start under that condition. We want to be sure that the train is in motion that the striker train is in motion before we start to lift the hammer. And that's the first thing that we're finding right there. Now, what do we find here? We find that by default that we're just about in time on this. Here is, let me roll this fly a little bit, this cam. If we can see this cam right here, our feeler is in that cam, centered down in the bottom. The strike has just ended. The third condition that we have to get correct is that we have dropped into the stop notch in the count wheel. And it looks like those three conditions are satisfied. Let's look a little further and see if we just lucked into that. If we cannot satisfy those conditions, here on the JB Ranch, Huckabee is retired, and this is a one-man shop. Lots of times it's a one-man household. I cut the camera here quick to make a little run to answer the telephone. My wife has gone out to have supper with some of the lady friends from our church, and it's about 6:35 p.m. Here on Tuesday night on the JB Ranch here in Austin, Texas. So that was the interruption we had. The thing that we were discussing is identifying how that we are in time. We find that as we drop into the deep slot in our cam, we must drop into the deep slot in the locking plate, and we must not be on the upstroke of the hammer. Must not be on the upstroke of the hammer. The hammer is totally unloaded, and I have another phone call. Let's review the conditions here again that we're looking for, and how we get there. The feeler must be in the center, centrally located in the space in the locking plate. The feeler here must be in the notch in the cam. The hammer must have cleanly passed over one of the lift pins. Now, if these conditions do not exist and an adjustment is required, we simply separate the plate slightly here, slightly in this area, turn here into the back, and we move one or two or three or the appropriate number of teeth, the relationship between the pinion and the gear that we have there. That sets the condition between the pinwheel and the third wheel. If we have a problem down in the lower section of the movement, we lift the plate down here, separate between the great wheel and the pinwheel, and move one or two or three positions there. Let's look at the strike mechanism right here. I'll hold a little torque on this. We'll place a winding key. This is a bench winding key on this square that the minute hand goes on. And as I turn this square here, I'm rolling the train. I'm rolling the train simply because we don't have the escapement set up. Let's turn this around like this, and we're approaching the point that's called warning. We're lifting the lever that goes through the center wheel. We can see the motion outside here. We lift this lever. We're raising the warning stop, and here we release the warning. The striker train advanced ever so slightly. We must not start lifting the hammer in that period of time. We turn a little further and we drop there, and we go into the strike. 2, 3, 4, 5, 6, 7, 8. Strike 8 times and we cut off in the locking plate. Simple as that. Refer to any text in striker clocks, any handbook or text on a striker clock. Follow the instructions in that, but disregard the words, the names that I've used here, because the names that I've used here may not be appropriate to this unit or to another. In the particular time that this was built, there was really no standardized names for the parts or the actions or the pieces. Most of the names that we consider to be standardized has been those names have been created since this movement was built. Let's look a little further about the taper pins. What do we do about those? These pins that I have here are brass pins, and we can just bump them into the into position like that. You can push them in with the tip of a plier. If they're shorter, you can do that with by biting the point of the plier. And we have a new one here and one here. For the time being, we will not cut those pins away. Purely for the aesthetic characteristics of it, we would cut off the excess in each one of them. The problem that we find is that we trim these pins down. The next man that tears the movement down, he will have to keep the pins in with the appropriate pillar, because the location of the holes in them is different in each one. Notice this pin here is, let's get where we can look at it. See, it tightens right in the center of the pin. All of these pins are the same size. This pin right up here, if we can get where we can see that, it's almost totally in to the pillar here, passes out over there. This one we only get in about 30%. Possibly we can see this pin coming down here. How about this one? This one gets about 80% through the pillar. Get the hammer out of the way. And this one gets about 40% in. We'll leave them where they are for the time being. Let's look at this hammer situation. We mentioned that on the back side is a spring, and here is the spring. That spring causes this hammer to bounce on its stop, tightens up that operation. And let's look at the escapement now. We'll need to put the escapement in. We shouldn't have any problem with this particular escapement because the depthing on it was correct when we disassemble this. So this will be as simple as dropping, being right-handed here, I need to change my hands. We'll just drop this escapement anchor on there, and the little latching wire, which is here, this little latching wire, we turn it around and set it over the pivot. We need to move it inward a little. We can come right in here and bend it in that space. Come over here, and there's the hole down. That'll fix that up. And the problem that we have in the process here, we've got the weight cords pretty much in a tangle. Now, we'll need to correct that. We don't want to leave that situation in the movement. If the tangle was not too bad, in 8 days it'd be down and we'd wind back again. But the thing we'll do, we'll just lift off the click spring, push the click back, and we'll reel the cable off. Reel off the cable, set the click spring back in place, and I need to lay this down to do that best. Set that back in place, and let's do the same thing. No, we don't need to do the same thing over here. This one enters there. So that's in good condition. I notice one of my J-bolts down here is loose. We'll tighten that up. All right. Now, one of the things that remains is getting our hammer back in place. Don't know just where that rod was. Let's just send it down here somewhere in about that direction. We'll form that up into position when we set the movement back into the case. I will be returning the movement to the case, and this clock has been in a storeroom for well, we've been living here on the ranch 19 years last summer, and this clock has been in a storeroom for that period of time. So all this grease is all dried up and whatnot, but we'll put it to running. Don't fret that situation. These old clocks with the loose pivots on them, whatnot, and well powered, we can set it to running and see the operation without cleaning or oiling at all. We won't have any problem in getting that to go. One of the things we want to do is to listen to the strike rate. Clocks built in this era strike extremely fast. This one goes bong, 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 about that fast. And that's the way that they were made. The gear trains were short, the flies were small, and that's the normal speed that they strike. When I make the setup to go back in the case, I have this case sitting in a small, low chair. I'm going to have a little trouble getting the camera down low enough. The tripod that I have, its lowest level is about 35 or 40 inches from the floor. But I'll go return this to the case and move the tripod, and just so that we can take a look. We'll set it up, set it in beat, and looking at the tape, I only have a couple of more minutes to discuss this movement, and the tape will end. I have placed this back into the case, strung the weight cords over the upper pulleys, the two sides here. I formed the hammer arm so that the hammer is appropriate for the gong, and started this running. Let's carry this to the next strike. It just struck 12, and here's the 1 o'clock strike. Go around again. We have the warning, which you can see on the wheel here, and then as we approach 1 hour, we get the 2 strike. Let's try this again. Watch for the warn right here at the pencil pointer. We warn about that distance before noon time, and here's the point of strike. Let's get the camera down a little lower. Look at the lower section. We'll back off our lens a little. Right here we see the striker weight. The time weight is just behind the edge of the door. We have a good pendulum motion here. Key that is with this. I imagine that it originally had a crank. Turn this and latch up. Let's look at the front door here for a moment. Raise the camera again. And move the lens off some. This front door, there's an interesting situation on it. Let me see if I can see this. Right at this point in the door, there's a large bubble in the glass. Here's a bubble, here's one, here's another. Here's one here, at this point, up here. All over this glass there are bubbles. When I obtained this clock, one of these molding strips was missing out here on the door. I don't recall which one, but I located a piece of wood that matched this and made that molding strip, and I had the glass out of the door. While I had that glass out of the door, I laid it on the flat workbench, and I noticed that it would not lie flat on the bench, and I discovered that that glass is not flat. I drew the conclusion that that is a piece of hand-blown glass where the bubble was blown by the glass blower. The bubble then was broken and let the glass flop onto the bench and later cut this out. And I'm pretty sure that this is a piece of hand-blown glass that we have on the door. Let's turn around here and see how we get the dial on. I'll go to about 6:30 there, and to install the dial, do a little job like this. You reach in here and pull these hands out here, slip up, turn these around, form the hands just a little bit, and let's go to the next hour and strike and see what we have. We're striking 5. We have this on 7. Now I have the option, and I bumped this pendulum rod and stopped that while this was going on there, but I have the option of moving this hand to 5 or go into the lower section and pull the little rod, advance the striker to 6, advance again to 7. Okay, we'll close the door here and let's look at this trim that's up on top. This trim that's up here was damaged when I obtained the clock, and I scraped around on it a little bit, and I found that this is made of plaster of Paris, or a gypsum-like material. I very carefully removed that from the wood, patched it up with some plaster of Paris, and sprayed it with a brass paint, and then glued it back in shape. This is plaster. The columns that's on the side of the case, these are wood turnings, but then they're overlaid with a little bit of plaster at the ends to obscure the wood grain. If we look down a little further, possibly we can see on this column right here, where this has been scratched and this has been scratched here, we can see the plaster that is underneath that. I believe that we're sitting on a low chair here. I believe that some form of foot was underneath this, the base here to begin with.